Hello, this is John Miares, and in this lesson, we are going to look at sine and cosine as functions of real numbers. As we are starting to see, by redefining our definition of an angle, we can explore sine, cosine, and tangent of functions of real numbers and not just ratios of side lengths in right triangles. If we're going to treat them as functions, like many of the other functions you dealt with in Math 121, we will need to explore their properties like their domains, their ranges, and their graphs. To get started, I'm going to open up a demonstration that I found uh, in Desmos that I believe should do a pretty good job of connecting the geometric interpretation of the sine and the cosine with the analytic interpretation as functions of real numbers. So what you're seeing here on the left is a unit circle. The radius is marked in green, and the intersection with the terminal side of the angle on the unit circle is marked with this little red shaded circle here. At the moment, the angle measures 0 degrees, and we know that the sine of 0 is 0 because you're calculating y over r. At this point here, y equals 0 and r equals 1, so the sine of 0 equals 0. Another way of looking at this from the perspective of SOHCAHTOA is that there is no opposite side in this reference triangle, and the hypotenuse will be 1. So the sine should be 0 over 1, opposite over hypotenuse. Now let's start moving the terminal side through quadrant 1. And let's take it up to about 30 degrees here. As we progress through quadrant 1, we begin to see that the opposite side of this reference triangle is going to be getting bigger and bigger. Since the sine function represents the opposite side over the hypotenuse, and that opposite side is getting bigger, then the functional values on the sine graph are also going to increase. Here, what we're seeing is that the sine of 30 degrees, or pi over 6 radians, is going to equal 1/2. As we increase the angle some more, let's say we go up to the sine of 45 degrees here, we're going to get sine of 45 degrees is the square root of 2 over 2. And as we progress to 60 degrees, we're going to get the square root of 3 over 2 as the sine of 60, or pi over 3. And as things get bigger and bigger, as we get really close to 90 degrees, let's stop here for a second before we get to 90 degrees. Here we are at 86 degrees. You can see in our reference triangle that the opposite side y, here, this little red segment, is almost equal to the length of the hypotenuse, but still slightly less than it. So the values of the sine function, y over r, are going to be slightly less than 1. Meanwhile, on the right-hand side over here, what you're seeing is that the graph of the sine function is getting closer and closer to 1. On the x-axis, you're measuring the angles in radians. On the y-axis, we're plotting the value of the sine function. Starting at 0, again, you have the sine of 0 equals 0. And as we get closer to 90 degrees, or pi over 2 radians, we're approaching the value of 1. If we go all the way to 90 degrees, the sine of 90 equals 1 because you have y over r, y equals 1, r equals 1, the ratio will equal 1. The y value equals the r value. If I'm looking at this from the perspective of SOHCAHTOA, the opposite side is essentially equal to the hypotenuse, even though we really don't have a reference triangle here to work with. Let's see what happens as we progress through quadrant 2. I'm going to increase this until we get to, let's say, 120 degrees there. Let's stop at 120 degrees for a bit. Now here, the opposite side y, this red segment, is still a positive length. But as we progress closer to 180 degrees, what you're going to see is that red segment length is getting smaller and smaller and smaller. And as we look on the graph on the right-hand side, you're also seeing the values of the function begin to decrease as we head towards pi radians or 180 degrees. Once we get to 180 degrees, actually, I'll stop just before 180 degrees. There still is a tiny reference triangle there. The opposite side, y, is almost 0. So as you take 0 divided by the 1, or almost 0 divided by 1, you're getting values that are really close to 0. And then right at 180 degrees, the y value is 0 divided by the r value of 1 will give you a sine function value of 0. So now we're seeing everything going on between 0 and 180 degrees, or between 0 and pi radians over here. Functional values starting at 0, they increase to 1 when we get up to 90 degrees, and then they're decreasing back to 0 when we get to 180 degrees or pi radians. Now let's progress into quadrant 3. What you're seeing here in our unit circle is that the y values are becoming negative, and the r value, the hypotenuse, is staying 1. And so as we progress towards 270 degrees, the values of the sine function y over r are getting closer and closer to -1. In our graph on the right, we see the corresponding decreases in the functional values as the angles progress through quadrant 3. So now by the time I get up to 270 degrees, we're going to be at the functional value. The graph will bottom out at -1. Let's continue through quadrant 4. As we work our way through quadrant 4, the y values are still going to be negative, but they're working their way back towards 0 as we get closer to 360 degrees. Once we get to 360 degrees, again, the y value will equal 0 at this point, and the r value still equals 1. This graph that you see here in blue is one cycle of what we call a sine wave. The graph starts at the origin, it increases till you get to a peak at pi over 2 radians. It comes back down to 0 at pi radians or 180 degrees. Then it decreases to -1 when you get down to 270 degrees. And then it works its way back towards 0 at 360 degrees or 2 pi radians. Now, I say this is one cycle of the graph. Unfortunately, this demo won't show you what happens after we get past 360 degrees, or what happens if we go in the negative direction. Well, as we head forward past 360 degrees, if you can imagine it, we're going to go around this circle again, and we're going to run into angles that are coterminal with ones that we already had. So the pattern that we saw happen between 0 and 360 is going to repeat itself between 360 and 720. It's going to continue up like this and then down and so on. Similarly, if we were to go backwards and head with angles in the negative direction, we would also see the same pattern occur, because any negative angle we see would be coterminal with one of these angles between 0 and 360. So this pattern of this little wave here is going to repeat itself continuously every 360 degrees every time we go around the unit circle. So the graph of the sine function is going to follow this same pattern of going up and down and up and down that we saw before when we were looking at it in Desmos. It won't matter if I'm going forward or backward, because this pattern is just going to keep repeating itself. Now that we see the pattern, let's see if we can talk about other properties of this graph and start thinking about it as a function of real numbers, where we can look at the domain, the range, any symmetry inherent in the graph, and any other patterns or properties in the basic shape that might allow us to determine how we can quickly generate sketches of these by hand. The domain of this function, f of x equals sine of x, is going to be all real numbers. Remember, the domain of a function is the set of all possible x values that can be substituted into a function in order to generate a real y value. We should always be able to calculate the ratio of y over r, opposite over hypotenuse, in our reference triangle. At worst, at the quadrantal angles where there is no opposite side, you can treat the opposite or y value as 0. So it's not like other functions which have domain restrictions built in, like you can't take the square root of a negative number, or you can't divide by 0, or you can only take the logarithm of a positive number. You can always take the sine of any real number, positive, negative, 0, anything. The range of any function, remember, is the set of all possible y values or outputs of the function. This is going to be restricted to numbers between -1 and 1 based on how the values are being derived. The sine of an angle can never be bigger than 1 or less than -1 because the opposite side in the reference triangle can never be bigger than the hypotenuse. Consequently, this graph is going to bounce back and forth between -1 and +1 forever in both directions. When asking about the symmetry of a function, we're going to be looking at whether or not the function is either odd or even. Remember, odd functions are symmetric to the origin, while even functions are symmetric to the y-axis. In this case, what we're going to be seeing is an odd function, as it has symmetry that will go through the origin. As this graph passes through the origin, right here, and any point on this graph xy, there is going to be a mirror image at this point, -x, -y. So, and that is basically how odd functions are created, that if I have the point xy over here, there's going to be a corresponding point -x, -y over here. As for other things that we should notice about this graph, it's going to repeat itself every 2 pi radians or every 360 degrees as the terminal side of the angle goes around the circle over and over and over again. The function starts at the origin and it's going to oscillate back and forth between -1 and 1, with the key transition points occurring at what would be the quadrantal angles 0, 90, 180, 270, 360, and so on. We see those transition points labeled here on the sketch above. Knowing the shape of this graph, starting at the origin, increasing to 90 degrees, and then decreasing back to 180 degrees, decreasing further to -1 at 270 degrees, and coming back up towards 0 at 360 degrees, may help us as we are starting to get ready to do our Mad Minute quizzes. It can also help us remember the ASTC pattern, the all skiers take chances, all sine, tangent, cosine pattern, where the sine function is going to be positive in quadrants 1 and 2, and the sine will be negative in quadrants 3 and 4. Now that we've looked at the sine function, let's go back to Desmos and look at the cosine function. Now remember, for cosine, you're looking at adjacent over hypotenuse, x over r. At 0 radians or 0 degrees, you're going to have the cosine value equal 1 because x equals 1 and r equals 1. So x over r is going to equal 1, and that will correspond to this point 0, 1, which will be our eventual graph of the cosine value up here. As we start progressing through the first quadrant, we're going to see that the adjacent side lengths are less than 1 now. But for angles that are at least close to 0, the adjacent side x is almost as large as the hypotenuse r. So the ratios are still going to be very close to 1. But as the angles start getting bigger, the x values are going to be getting smaller and smaller, and my cosine value is going to be getting closer and closer to 0. Let's stop at 60 degrees for a second. What we're measuring here, of course, what you're seeing is the red adjacent side of this triangle is becoming the y value of this function as we graph it. As we get closer to 90 degrees, let's not quite get to 90 degrees. Let's stop just before 90 degrees. The adjacent side length is almost zero. And so the ratio of the adjacent side of the hypotenuse is going to be getting closer and closer to zero. Once we get to 90 degrees exactly, it's going to equal zero because there isn't any adjacent side in my little reference triangle anymore. X over r becomes 0 over 1. And now what we have here is the corresponding point, 90 degrees or pi over 2, comma, 0. As we progress into quadrant 2, the x values on our reference triangle are going to become negative. So the r hypotenuse, though, of course, is still going to be positive. So as we get closer to 180 degrees, the ratio of the adjacent side over the hypotenuse, x over r, is going to be getting closer and closer to -1 until we get to 180 degrees exactly, when it's going to equal -1. Going into quadrant 3, the x values are going to remain negative, but are getting closer to 0 again as they approach the 270 degree or 3 pi over 2 mark. So here we are now. Let's get to 270 degrees. The x value is 0. The r value is 1. That's going to divide x over r will be 0 over 1. And I'm going to have the point here, 3 pi over 2, comma, 0. Finally, as we pass through 270 degrees and head towards 360 degrees, the x values are becoming positive again and are slowly increasing as we get towards 360 degrees, when x over r will equal 1 again. Again, unfortunately, this demonstration won't show it, but if we were to continue around the unit circle past 360 degrees, or if we were to head in the negative direction, this pattern will repeat itself over and over again every 360 degrees or 2 pi radians. So this shape here is the basic shape of the cosine wave. It has many of the same patterns that we saw with the sine wave. And when we consider how the sine and cosine are related to each other, it should seem reasonable that you would get similar behavior between the two functions. Let's look at some of the analytic properties of the cosine graph. Just like with the sine function, the domain of the cosine function will be all real numbers. There won't be any angle we can't compute a cosine value for, whether it's positive, negative, or 0. The range, just like the sine function, will be between -1 and 1, as the adjacent side of the reference triangle can never be larger than the hypotenuse. Symmetry this time will be over the y-axis, making this an even function. For any xy value, what we're going to see is that there will be, for this point here, and this point, let's say here, for any value that I might label on my graph as x, y, there will be a corresponding mirror image at -x, comma, y. And if that holds true for all values in the domain of the function, then we define this as an even function. That is what is going to generate the symmetry over the y-axis. As for other patterns or pieces of this graph, we again will see that this pattern will repeat itself every 360 degrees or every 2 pi radians. Also, it's going to oscillate between -1 and 1, just like the sine wave. And the key transition points are going to occur at the quadrantal angles as shown above. The big difference between sine and cosine is that the cosine wave is going to start at the peak of the wave at x equals 0 compared to the sine wave, which started at the origin. Again, the nature of the shape of this graph can be another way we can try to prepare for our mad minutes. The cosine function is going to be positive in quadrant 1, and it's going to then head negative in quadrants 2 and 3, and then it will become positive again in quadrant 4. Before we continue on to looking at the graph of sine and cosine functions, I want to step back and do a quick review of sketching other functions and using what many textbooks refer to as the basic shape method to graph a function by first looking at its basic shape, then taking separately into consideration the effect of adding, subtracting, multiplying, or dividing different constants to the function itself. Let's say I ask you to graph the functions y equals x squared and y equals negative 2 times the quantity x minus 3 squared plus 2. We should know from our previous experiences that the graph of y equals x squared is a basic parabola with its vertex at the origin 0, 0, and the key points are going to be following the squaring pattern, where 1 squared equals 1, 2 squared equals 4, 3 squared equals 9, and so on, with those same points repeating themselves in the negative direction. When we want to sketch the second function here, y equals negative 2 times the quantity x minus 3 squared plus 2, we see that it should also have a parabolic shape to it because other than the constants, it basically will degenerate into a quadratic function with y equals something squared. If we were to generate this on a calculator or in a utility like Desmos, we would get a graph that looks something like this. But what I want to look at specifically here is why this blue parabola has the shape that it does and why the vertex is where it is. First, the negative 2 in front of that entire expression serves two purposes. By making what we are squaring negative, the parabola is going to turn itself upside down. Also, by doubling the values being squared, the blue parabola is going to be twice as steep as the red parabola. So instead of first going over 1, up 1, then over 1 more, up 3 more, in this blue parabola, we're going over 1, down 2, and then over 1 more, down 6. The minus 3 inside the parentheses is going to shift the parabola to the right by 3 units. We saw this behavior when we were working with conic sections back in the first few weeks of this class. Meanwhile, the plus 2 on the end is going to make the graph move up 2 from where it should be. So if I was to ask you to graph this function by hand, you could say to yourself, well, I have to take the basic shape of the parabola that I have, flip it upside down, make it twice as steep, move it to the right 3, and then move it up 2, and I'll have the correct graph. Let's look at a similar example here. Here I'm asking you to compare the cube root of x to the cube root of the quantity x plus 4 minus 1. The cube root function looks like this. It passes through the origin because the cube root of 0 is 0. As we head in the positive direction, you'll see it passes through the point 1, 1. And as we continue on to the right, it will rise ever so slowly as x gets large. So you'd have the point 8, 2, the point 27, 3, the point 64, 4, and so on. In the negative direction, I have the point negative 1, and then we'll have other points that will be symmetric through the origin as it travels through to the left. Negative 8, negative 2, negative 27, negative 3, negative 64, negative 4. The second function at its core is also a cube root function, so the basic shape will share that of the original cube root function. Graphing this on a calculator or again in a utility like Desmos will give you the following here. The plus 4 under the radical sign is going to cause the graph to shift left 4, while the minus 1 outside the radical sign will shift the graph downward by 1 unit. Because there is no coefficient in front of the radical sign, the shape of the curve does not get dilated or stretched like we saw with the parabola in the previous example. So the other points on the graph are in the same relative location as they were on the original cube root function. Instead of the point -1, -1, we have the point -5, -2. Instead of the point 0, 0, we have the point -4, -1. Or instead of the point 1, 1, we have the point -3, 0. What we've demonstrated with taking the basic shape of a graph and moving it left, right, up or down, stretching it, shrinking it, flipping it upside down, or keeping it the same direction is at the core of what we call the basic shape method for graphing functions. Let's suppose that f of x is a simple function whose graph has what we call a basic shape. This simple function could be a monomial like y equals x squared or y equals x cubed. It could be a radical function like the square root of x or the cube root of x. It could be a more complex function like y equals e to the x or y equals the natural log of x. What we can say is if we are given a function to graph that is in the form y equals a times f of the quantity x minus h plus k, then those constants here, a, h, and k, are going to have a certain effect on the basic shape of the graph. The lead coefficient a will affect the steepness of the graph. If a is bigger than 1, the y values will stretch higher. If the values of a are less than 1, then they will shrink and go flatter. If we change the sign of a from positive to negative, the graph will flip upside down. If there's an h subtracted inside the parentheses, then the graph is going to shift horizontally. For values of h that are positive, so it becomes x minus h, the graph will shift to the right. Whereas if it looks like x plus h, because h is a negative number, you're taking x minus negative h, which turns into x plus h, the graph will shift to the left. For values of k being added or subtracted outside of the function, the graph is going to shift vertically. If we're adding k, the graph moves upward. If we're subtracting k or adding a negative value of k, then the graph is going to shift downward. All the while, the basic shape of the graph, be it a parabola or a J curve or a cubic pattern, is going to remain the same. Why don't you think about this one on your own for a bit? Let's say you were asked to compare y equals the square root of x to y equals 2 times the square root of the quantity x plus 3, all plus 1. See if you can identify what each of those constants does to the graph here, which is the basic shape of y equals the square root of x, and then try to figure out what the graph of the new function should look like. Go ahead and pause this video for a few minutes to see if you can figure out what's going on with this one. All right, let's look at the different pieces here. The 2 on the outside is going to make the graph twice as steep as it was before. So if we look at this red graph where the points are going up vertically, first 1 unit as we travel out to the right for every of the next perfect squares, this time in our new graph, the graph is going to be going up 2 units every time I move over to the next level perfect square. The 3 under the radical is going to shift everything over to the left by 3 units, and the plus 1 on the outside of the graph is going to move the graph up 1 unit. So when we sketch our new graph, it will look something like this, where our new starting point that was at 0, 0 has been shifted to the left 3, up 1. And then where before I was going over 1, up 1, then over 3, up 1. Here I'm going over 1, up 2, over 3, up 2 to get to my next point. So this blue curve is now twice as steep as my red curve. That's affected by the 2 in the front. The plus 3 is the shift left, and the plus 1 on the outside moves the graph up 1. Now, the basic shape method can be extended to trigonometric functions as well as it was to these functions that we just looked at. For now, we're going to concentrate our efforts on just the sine function and the cosine function and look at the effects of putting a lead coefficient in front A, coefficient in front of the x term, B, subtracting a quantity inside the parentheses, which we'll call C, and adding a quantity to the end, which we'll call D. The lead coefficient A affects what we call the amplitude of the graph. As much as the lead coefficient in other functions affects the steepness of the graph, this coefficient is going to tell you how far the graph is going to rise above the equilibrium level or the middle of the graph. For example, in a basic sine and cosine wave, the amplitude of the wave is 1 because the graph goes up 1 and down 1 from the x-axis. If we put a 2 in the front, say made this y equals 2 sine x, then the graph will go up 2 to its peak and down 2 to its low point, which we call the trough. If I put a 5 in front, so it was like y equals 5 cosine x, then the graph will have a peak at y equals 5, and it will have a trough dip down as low as -5. Now, if a were negative, the graph is going to flip upside down, just like when we were looking at other functions. But the amplitude will always be a positive number, which is why you see these absolute value signs around the A up here. So if the lead coefficient, for example, is -3, I'm looking at y equals -3 sine x. The amplitude of the wave will be -3 because you're going to go down to -3 and up as high as +3. But the graph is going to open upside down from its basic shape. So instead of starting at the origin and working its way up, it will start at the origin, work its way down. If it were for a cosine graph, let's say I have y equals -4 cosine x, it will be flipped upside down. It will start at its trough at 0, -4, and then it will work its way back up to a peak at y equals 4 when the radian measure of the angle is pi radians, or we're at 180 degrees. The b value in front of that x expression is often referred to as the frequency of the graph, and it tells you how many cycles or waves can be drawn in a length of 2 pi radians along the x-axis. For a basic sine or cosine wave, the number of cycles that can be drawn is 1. That the full cycle starts at 0 radians and ends up at 2 pi radians, or it start at 0 degrees to 360 degrees is when you're going to be able to get the full cycle. If the b value were 2, so we're looking at the sine of 2x or the cosine of 2x, then we would compress the wave so you could fit 2 full cycles between 0 and 2 pi. If the b value were 1/2, so it was the sine of a half x or the cosine of a half x, then you would only be able to draw a half cycle between 0 and 2 pi. The C value is referred to in this graph as the phase shift, and it determines the horizontal shift in the graph. Just like with other functions that we've worked with, if you see it as x minus some constant value c, then the graph is going to be shifted to the right. But if you have x plus c inside the parentheses, meaning you're subtracting a negative value of c, you're shifting the graph to the left. The value of D is referred to as the axis of oscillation or the axis of equilibrium. It is the vertical center of the wave. For the basic sine and cosine waves, the axis of oscillation is going to be the x-axis. But if we were to add 2 onto the end, say looking at the function y equals sine of x plus 2, then the axis of oscillation would be the horizontal line y equals 2, and it would shift the entire sine wave up 2. If we were to subtract 4 on the end for our value of d, so the function looked like y equals cosine of x minus 4, then the axis of oscillation would be at y equals -4. The amplitude is going to always be measured how high above or how low below the axis of oscillation will be when we rise or fall. Now, one very important thing I need to note is that in several textbooks, including ours, they define the standard equation of the sine waves and the cosine waves with the b value distributed through the parentheses. So your function will look like a times the sine of the quantity bx minus c. Whereas what I've done, if you look up above here, I've factored out this b and left the c alone. What I would recommend if you see a problem like this where the b has been distributed through the parentheses, the very first thing you should probably do is factor the b out so that you can readily identify what that phase shift is. Otherwise, you're going to have to adjust for the phase shift by taking this c value and dividing by the b value. If there's nothing in front of the x inside the parentheses, so this is just a 1 here, then the value of c will be your phase shift or your horizontal shift. Let's look at a couple of examples together. Suppose I want to sketch the graph of the function y equals the sine of x minus 2, as I mentioned on the previous slide. Let's start with the basic shape of the graph of y equals the sine of x. Since the negative 2 is on the outside of everything, there is nothing being multiplied and there's no other sets of parentheses. The only thing that's going to change here is the axis of oscillation is going to move downward to y equals negative 2, or the entire graph of the sine wave is going to shift down 2. This is going to make our graph look like this. What if we want to look at y equals 3 times the sine of x? The 3 on the outside suggests we are going to take the basic shape of the sine wave here and we want to stretch it vertically by a factor of 3 to make it 3 times steeper so that our amplitude is going to equal 3. The graph of y equals 3 sine x compared to the basic shape is going to look like this, having the same starting and ending points at 0, 0, and at 2 pi 0. But instead of going up 1, down 1, like with just y equals sine of x, you're going to go up 3, down 3 from the x axis. Let's look at a few more simple examples. For the cosine of the quantity x minus pi over 6, because of where the pi over 6 lies, we're going to take our basic shape for the cosine and we're going to shift it over to the right by pi over 6 radians or 30 degrees, which will make our graph look like this. The peak of the graph, instead of being at the point 0, 1, will now be at the point pi over 6, comma 1. The end of the cycle, which would have been at 2 pi comma 0, will now be at 13 pi over 6, or 2 and a sixth pi comma 0. Otherwise, the basic shape of the cosine wave remains the same. The amplitude is still 1, the wavelength is still 2 pi, just everything's been shifted over to the right by pi over 6 radians. Let's try one last one together. Let's say I'm looking at y equals the sine of 3x. We want to figure out how that 3 is going to affect our basic shape of y equals the sine of x. We called the b value in front of the x the frequency of the wave, which basically meant that we could hope to complete 3 full cycles between 0 and 2 pi. This is because as we're computing the values of the sine, the 3 in front of the x is making the angle on our, as we're going around the unit circle, 3 times bigger than it normally would be. So each cycle of the graph is going to be 120 degrees or 2 pi over 3 radians. So our graph is going to look like this. We see here in green that the graph goes through 3 full cycles between 0 and 2 pi. That'll be compared to our shape in red, which just goes 1 cycle between 0 and 2 pi. So our wavelength here, the length of one of these cycles, has been cut by a factor 1/3. So normally where one full cycle would have gone from 0 to 2 pi, the full cycle on this graph will go from 0 to 2 pi over 3. There is a relationship between the frequency value and the wavelength that can be checked. For the basic shape, the red graph, the normal wavelength of y equals sine of x, also called the period of the wave, is 2 pi radians, 360 degrees. If we take 2 pi divided by the b value, 3, you will get the wavelength for one cycle of our new graph, which is labeled with this symbol here is the Greek letter lambda. Alternatively, if you know the wavelength, you can use it to find the b value by taking 2 pi and dividing it by the wavelength. This relationship between the wavelength and the frequency is an inverse one, meaning as the b value gets bigger, the wavelength is going to get smaller, and similarly, as b gets smaller, the wavelength is going to get bigger. The value 2 pi serves as what we call the constant of proportionality in this relationship. Now let's look at what we would have to do if we wanted to combine multiple transformations into the same problem. Suppose we have this function here, y equals -3 times the sine of the quantity 4x minus pi plus 2. Before we try to sketch this and identify the properties of the graph, I first would have to factor the b value out here and rewrite this equation as y equals -3 times the sine of 4 times the quantity x minus pi over 4 plus 2. Having this in factored form will make some of our downstream computations much easier to work with. Now let's look at each one piece at a time. The lead coefficient A is -3, which means the amplitude is going to be 3. So the graph is going to go up and down 3 from wherever the middle, the axis of oscillation, turns out to be. The negative sign in front of there, making it -3, will flip the graph upside down. So where the sine wave normally starts at the origin and goes up, this one is going to start downward from wherever the origin gets relocated to. The frequency value, B, will be 4, meaning we can fit 4 full cycles in a span of 2 pi along the horizontal axis. Knowing that a normal cycle has a length of 2 pi, to have a frequency of 4 means that our wavelength lambda will be 2 pi divided by 4, or reduced to pi over 2. The C value, the horizontal shift, the phase shift, will be pi over 4. Since we're subtracting pi over 4 inside the parentheses, we're going to move the graph over to the right by pi over 4 units. Finally, D, our axis of oscillation, will be at y equals 2, which means the entire wave has been shifted up 2. Now that we've identified what the properties of this graph are, we're going to need to know how to sketch it by hand, incorporating all the different pieces. Here's the way I would recommend working with this. The first thing I would do is start with the axis of oscillation, y equals 2, and graph that. Then we're going to, based on the amplitude, determine where the peak and the trough for this wave are going to be. Since we said the amplitude was 3, the graph is going to rise 3 above the axis of oscillation y equals 2, and then it will fall 3 below that axis as well. Next, we can use the phase shift c and the wavelength lambda and the basic shape to determine where the graph is going to start and end with its first cycle. Knowing this is a sine wave, which normally starts at the origin, the graph of this is going to have a similar behavior, starting at the axis of oscillation and ending horizontally pi over 2 units away from where it started. From there, we can sketch the graph and label key points based on symmetry and location of the transform quadrantal angles. This might make more sense if we see it in action. So here's my blank graph, and for reference, I am going to draw a quick sketch of the basic function y equals sine of x. To sketch our desired function, the first thing I said we needed to do was find the axis of oscillation, which is going to be at y equals 2 because of this plus 2 on the end. So I'm going to draw an orange dashed line right here. The next thing we said we would need to do was look at the amplitude to figure out where the graph was going to have its peak and where it would have its trough. Since the amplitude is 3, the graph is going to go 3 above and 3 below the axis of oscillation. So the graph is going to peak at y equals 5 and it'll dip as low as y equals -1. And I've marked those points with these two green dashed lines here. Next, let's figure out where this graph is going to start. Based on the constants being added or subtracted in this function, the wave is going to start pi over 4 units to the right and up 2 units from the origin. So I'm going to plot that point here over pi over 4 up to here. Next, we said because the b value was 4, the wavelength was going to be 2 pi over 4, which puts the end of the wave here at 3 pi over 4, comma 2. Now note, the horizontal distance between this starting point and the ending point of the wave is going to be pi over 2. 3 pi over 4 minus pi over 4 equals pi over 2. Next, we need to sketch this graph. The negative sign in the front suggests it's going to be heading downward from its starting point instead of upward. So you should have something that looks like this. From its starting point, it's going to go down as low as -1, and it's going to rise back up here to the axis of oscillation at y equals 2, and then it's going to peak at y equals 5, and then it will dip down as low as 2 again before starting the cycle back over again. The points themselves are picked up from the inherent symmetry in the wave itself. For example, this point right here, where it transitions from down up to up down, is the halfway point between pi over 4 and 3 pi over 4, making it pi over 2. The trough and the peak would have represented 1/4 of the way around the cycle and 3/4 of the way around the cycle. So I'm going to look halfway between 1/4 pi and half a pi will give me 3/8 pi. And then the halfway point between a half pi and 3/4 pi will be 5/8 pi. But generally, you can just divide this length between the starting point and the ending point by 4, and then use that to figure out where we should have our transitional points. Here's another one, but this graph is going to look at the cosine wave. The function itself is going to be y equals 1/2 times the quantity cosine of pi x plus 2 pi minus 4. Again, we will want to factor out the pi in front of the x so we can more easily identify the phase shift. Doing so gives us y equals 1/2 times the cosine of pi times the quantity x plus 2, then all minus 4. Let's try to identify the properties of this graph. The amplitude is going to be 1/2 because of the 1/2 out in front of the cosine. That will make the graph go up 1/2 and down 1/2 from the axis of oscillation. The frequency value, B, is going to be pi, which suggests that we should be able to draw pi full cycles between 0 and 2 pi. Now, that doesn't necessarily make sense in context, so we might actually look at this from what should the wavelength be. The wavelength is going to be determined by taking 2 pi over b, which if I divide 2 pi by pi, you'll get 2. So the length of one full cycle is going to be 2 radians, not 2 pi radians, 2 radians. This could affect how we do set up and label our graphs, though, so keep that in mind. The phase shift is going to be 2 units to the left. Again, not 2 pi units, 2 units. And the axis of oscillation is going to be at y equals -4, meaning the graph will be shifted downward 4 units from the y-axis. So let's set up our graph. Here again is the basic shape of the cosine wave from 0 to 2 pi with the key points labeled at the quadrantal angles so we can use them for reference. The axis of oscillation of the graph I want to sketch will be at -4. So let's graph that down here with an orange dash line. The amplitude is going to be 1/2, which means that the graph is going to go up 1/2 and down 1/2 from that axis of oscillation. So I have a green line dashed here at y equals -3.5, and I have another green dash line at y equals -4.5. The phase shift is going to be -2, or rather, we're going to be moving 2 units to the left because of the +2 inside the parentheses, which means our starting point for this first cycle is going to be here at -2, -3.5. We know that the cosine wave normally starts at its peak, but we're going to shift the peak 2 units to the left from where it should have been based on that +2. Next, the B value being pi means that the wavelength is going to be 2. So we're going to plot this point here that is 2 units to the right of our starting point. So we're at 0, -3.5 will be the end point of our first cycle of this cosine wave. Finally, let's draw in our basic shape and label the key points based on the inherent symmetry within the graph. The trough of the wave is normally halfway between the endpoints, so that's going to be here at -1, -4.5. The points where the graph crosses the axis of equilibrium are going to be -1.5, -4, and -1/2, -4. Now let's look at some examples where we are doing this process backwards, starting with a graph and trying to determine the function from whence it came, or in this case, two different functions, one involving sine, one involving cosine. Let's say that this is the graph that we're working with. What we should probably first do is see if we can identify the properties that will determine its equation, including the amplitude, the period, the phase shift, and the axis of oscillation. When we were graphing these from the equation, we started with the axis of oscillation, so we can start there as well. What I see is this graph has a peak at 3 and a trough at -1. So the axis of oscillation should be at y equals 1 right here. The amplitude is determined by seeing how far above or below the graph rises and falls with respect to the axis of equilibrium. As we noted here, that the graph has its peak at y equals 3 and a trough at -1, which is going to mean that a is going to equal 2 because we're going up 2, down 2 from the axis of oscillation. The wavelength is measured horizontally the length of one full cycle. The easiest way I usually like to measure these is by going from peak to peak or from trough to trough. And as I measure here, what you're going to see here is that the first peak is at 0 and the second peak is at 4 pi. So the wavelength is going to be 4 pi. That's going to make the B value, when I say B is always 2 pi divided by the wavelength, 2 pi divided by 4 pi will reduce to 1/2. Again, if we call the frequency of the graph B and tells us how many cycles I can fit horizontally between 0 and 2 pi, which you should be able to see here is since the entire wavelength is 4 pi, we're only fitting half the wavelength between 0 and 2 pi. Lastly, we need to look at the phase shift, and that's a little bit tougher to see. The phase shift is going to be dependent upon whether or not we want to call this a sine wave or a cosine wave. Cosine wave normally starts when x equals 0, it will be at its peak. So if I call this a cosine wave, then there is no horizontal shift because on this graph, we have a peak at x equals 0. So I could now take my pieces here with the d equals 1, the a equals 2, the b equals a half, and no phase shift. The equation of my graph could be described as y equals 2 times cosine of 1 half x plus 1. Of course, I also asked you to have this determined to be a sine graph. And for a sine graph, we need to normally see that this is starting at the axis of equilibrium. And that point would be right here at negative pi. So the sine wave is shifted to the left pi units. So the c value could be plus pi inside the parentheses, making your equation y equals 2 times the sine of 1 half times x plus pi plus 1. Now, literally, there are an infinite number of answers that we could use for this that would only depend upon whether or not you want to use a sine wave or a cosine wave, whether you want to use a phase shift or not, whether you want to flip the graph upside down to get it to fit the way that you want. But this is just a couple of simple ways that we can approach it here. I always try to look for the cosine first because it's much easier to find the peak of the graph than it is to find that point of equilibrium on the graph here. One that perhaps you can try on your own. Find the equations of two equivalent periodic functions, one involving sine, one involving cosine, that represent this graph below. Go ahead and pause the video to see if you can try this one for yourself first. Just like the one on the previous slide, start by finding the axis of oscillation, then the amplitude, then the wavelength, then the phase shift. All right, the peak of this graph is going to be at y equals 2. The trough is going to be at y equals negative 4. So when I'm looking for the axis of oscillation, that's going to be halfway between those two values here at y equals negative 1. To find the amplitude, we need to realize that if the peak is at y equals 2 and the trough is at negative 4, then you're going up 3, down 3 from the axis of oscillation, which is going to make the amplitude equal 3. For the period or the wavelength, we see we have the graph, the first peak starting at x equals 0, and I have another peak at x equals pi. So that's going to make my wavelength pi. To compute the value of b for this equation, then, we will take 2 pi divided by the wavelength pi, which will reduce to just 2. As for the phase shift, just like in the last one, if I call this a cosine wave, then there is no phase shift because the cosine normally starts at its peak when x equals 0, which is what we see here. Putting this all together with the other components is going to give us the equation y equals 3 times the cosine of 2x minus 1. The 3 coming from the amplitude, the 2 coming from the fact that the wavelength is pi, which is half of a normal cycle, so the b value is going to be 2, and the minus 1 coming from the fact that the axis of oscillation is at y equals negative 1. If we were to call this a sine wave instead of a cosine wave, that's going to be a little harder to find because it appears that the wave crosses the axis of oscillation somewhere over here. Try drawing that in. Here. And that point isn't very clearly labeled, but if I'm looking at basic symmetry here, I'm going to guess that that's at negative pi over 4. So we're going to assume that that's going to be shifted to the left by pi over 4 radians. So now your new equation is going to become y equals 3 times the sine of 2 times the quantity x plus pi over 4 minus 1. Now, again, there are multiple possible answers to this, but these are going to be probably the simplest ones to find. Additionally, if I didn't have to find both a sine function and a cosine function, my preference is going to always be to solve for the cosine because it's always going to be easier to find the peak of the graph up here than it is going to be to find that equilibrium point here. So given the choice, always try to find the cosine wave values first. One of the real world applications of sine waves and cosine waves is that they are great for modeling what we call periodic behavior. If something is oscillating in a wave pattern over time, like a spring or a pendulum, then sine and cosine waves are great for finding equations that model their motion. Radio waves and sound waves can also find their roots in sine and cosine as terms of modeling them as well. Here's an example of one that is very similar to what's on the homework. A buoy bobs up and down in simple harmonic motion as waves pass it. A particular buoy moves 4.2 feet from its highest point to its lowest point and then returns to its highest point every 12 seconds. Find an equation for the motion of the buoy. Assume that it's at its highest point when t equals 0. The first thing we should probably do is try to draw a graph of this situation. Let's assume that at equilibrium level, we are going to be a calm sea. I'm going to call that right here at y equals 0. For a graph to travel a total of 4.2 feet from its highest point to its lowest point every 12 seconds will mean that it's going to travel from a peak of about 2.1 to a low of 2.1 below equilibrium every 12 seconds. So, assuming that we are starting at its peak at t equals 0, that means I'm going to have my graph start at what will be the point 0, comma 2.1, and it will end at the point 12, comma 2.1. So here's what my graph is going to look like in general. And of course, in the real world, this graph might need to be adjusted if we were somewhere above or below sea level. But for now, what we're going to just say here is that equilibrium level, sea level, is going to be 0. Our axis of oscillation, 0. The amplitude, I am going 2.1 feet above the axis of oscillation, 2.1 feet below the axis of oscillation. So if I'm peaking at 2.1, my trough is at 2.1, that means that my amplitude is going to be 2.1. The period, the wavelength, it is going to complete one full cycle going from its peak to its low point and back to its peak in 12 seconds. So I'm going to say that the period is going to be 12 seconds. Consequently, the b value will be 2 pi divided by the wavelength, which will just be pi over 6. Finally, we need to look at the phase shift. Seeing that this graph has its peak when x equals 0, we can just call it a cosine wave with no shift to it. So putting this all together is going to give us a function y equals 2.1 times the cosine of pi over 6t. 2.1 coming from the amplitude, pi over 6 coming from taking the 2 pi over 12 in our wavelength. And by using cosine, there is no phase shift. By saying our axis of equilibrium is at y equals 0, there's going to be no different d value either. So this function here is our final answer that will model the motion of this buoy. Here's one more we can work through together. Suppose that after you are loaded into a Ferris wheel car, the wheel begins turning at 4 revolutions per minute. The wheel has a diameter of 12 meters, and the bottom seat of the wheel is 1 meter above the ground. Express the height h of the seat above the ground as a function of time t seconds after it begins turning. Here is a picture of a sample Ferris wheel. We're told that the diameter of the wheel is 12 meters and that the bottom seat is 1 meter above the ground. That is going to make the peak height of the Ferris wheel be 13 meters, and the height of the axle, which will be our equilibrium level halfway between the peak and the trough, at 7 meters. So let's try seeing if we can come up with an equation that will model this scenario. The axis of oscillation will be at 7 meters because that's halfway between the peak and the low point on the Ferris wheel. To find the amplitude, we need to see that if the peak is at 13 meters above the ground and the trough is 1 meter above the ground, the amplitude is going to be 6 because you're going up 6, down 6 from that equilibrium height of 7 meters. The wavelength is going to be how much time it takes to go through one full revolution. We're told that the wheel rotates 4 revolutions every minute. So with 1 minute being 60 seconds, that's going to make each revolution take 15 seconds. So that's going to be our wavelength, lambda equals 15. To get the B value, we're going to take 2 pi divided by our wavelength, 15, which doesn't really divide out well, so we're just going to leave it as the fraction 2 pi over 15. As for the phase shift, well, let's think about the behavior here. If we're starting at t equals 0 as the point when we're first getting on the Ferris wheel, that means we're starting at the bottom of our wave and working our way around. So this appears to be, if the trough is at 0 instead of the peak being at 0, this will become an upside down cosine wave. But we would not need to do any phase shift at all because time 0 normally cosine's at its peak. If I just flip it upside down, the starting point will be at its trough. So incorporating all this all together, we have the function h of t will be negative 6 times the cosine of 2 pi over 15 times t plus 7. Negative because I'm starting at the trough instead of starting at the peak. 6 is the amplitude. 2 pi over 15 is going to be 2 pi divided by the wavelength. The plus 7 is because my axis of oscillation is going to be 7. Nothing being added or subtracted to the t because there is no phase shift. There's one more example I want to look at that will not show up on your quest, but could possibly be on the homework. I'm not going to push this idea very hard because graphing calculators make this kind of exercise fairly simple. But let's say you were asked to draw a rough sketch of y equals cosine 2x plus 2 cosine x using a process they call addition of ordinates. Well, ordinates refer to the y coordinates of points on a graph. So what they're talking about is we're going to look at the two parts of this graph separately. We've got y equals cosine 2x and y equals 2 cosine x. We'll try about graphing them separately and then seeing if we can add together their corresponding y values for the matching x values. So to demonstrate, let's first sketch a graph of y equals cosine of 2x. Here you see what we have is a cosine wave with a period of pi and an amplitude of 1. I've also labeled a few key points here so that we can see what values we're working with. On this same graph, I'm going to have y equals 2 cosine x in blue, which has an amplitude of 2 and a period of 2 pi. Again, I'll label some points here for reference for now. The function I want to sketch is the sum of these two, y equals cosine 2x plus 2 cosine x. And generally what we would want to do is add the y values together for every corresponding x and then connect the dots. So for example, on the red graph, here I have the point 0, 1, and on the blue graph, I have the point 0, 2. When I add them together, we get the point 0, 3. We go to x equals pi over 4. On the red graph, you're at 0, and on the blue graph, I'm at the square root of 2. So when I add these together, you're going to be at the square root of 2. When I go to pi over 2, now my red graph is at negative 1, and my blue graph is at 0. So when I add those together, we're going to be on the green graph at negative 1. For x equals 3 pi over 4, my red graph is back up to 0. My blue graph is down to negative square root of 2. So when I add them together, you're going to get negative square root of 2. Finally, at x equals pi, on the red graph, we're at y equals 1. On the blue graph, I'm at y equals negative 2. So when I add negative 2 plus 1, you're going to get to y equals negative 1. Again, this process is much easier to do with a graphing calculator, and I don't know of any problems where I'm going to ask you to have to do this process by hand. But what I will say is if you see these instructions that say addition of ordinates, basically this is what we're talking about. And for all intents and purposes, you can just sketch these on your calculator, trace the key points, and we'll call it good. So, as a general rule, I like to keep my lecture videos under 1 hour so that I can say that time you spend watching videos is going to be equivalent to the time spent listening to my lectures and taking notes. And I know this one is definitely going to be more than an hour. What I can say is that the next lecture is going to be much shorter because it doesn't have much material to it, and I shouldn't need to go into the level of detail that I did here with these graphs of sine and cosine. Anyway, here are the problem challenge problems for section 5.3. Hopefully you'll be able to get through them without too much difficulty. But if you do have any questions, you have my email, you have the discussion boards, you have each other to work on as resources and to check each other's work on. So hopefully it won't be so bad. Thanks for watching, and we'll see you all soon.